40. Calculate the delta G notch for each of the following reactions from the equilibrium constant at the temperature given. Okay, so we have vaporization of water, liquid water turning into gaseous water. Okay, they gave me a temp, 60 degrees Celsius. That's pretty low, right? Usually water becomes steam at 100 degrees, so this is interesting. And a Kp of 0.196. Okay, so let's find out. What is that delta G? What's that Gibbs free energy, right? Now, for this one, we can kind of guesstimate if this is going to be spontaneous or non-spontaneous. We're trying to turn water into a gas below its boiling point. Chances are that's not happening, right? That's not happening naturally. So we can kind of guesstimate that this guy, or not this guy, but this delta G value is probably going to be a positive value because it's non-spontaneous, right? Things that are non-spontaneous needs some extra external amount of energy to make this actually happen. So that's what we're banking on. Let's see if we're correct at the end. Now, when they give you an equilibrium constant and you're solving for the delta G, there's basically only one formula that we're going to use, and it's this right here. Delta G equals negative RT ln of K. Now, in the specific problem, they give me a Kp, right? But in here, I only wrote down a K because you could use any K value. Ka, sure. Kb, you got it. Kc, most definitely. Keq, alrighty then. Where's that from? Alrighty then. Anyway, we'll just keep going. But anyway, we're going to plug in the K value of 0.196. Now I just need to know what that R and the T value is. Well, the R is a constant value, 8.314. You probably have to memorize that. And the units, if we're using 8.314, is joules per mole times Kelvin. But it's in Kelvin, so the temperature that we have to use is also in Kelvin, but they gave it to me in Celsius. So the first thing I'm going to do is I'm just going to convert that Celsius into Kelvin by adding 273. More specifically, I'll add the more specific number, 273.15. So 273.15 plus 60 is 333.15. 333.15. Oh, I don't know why I wrote a K there. Sometimes my brain just, I don't know, sees the K and then just writes it down. But anyway, 333.15, that's going in for the temperature. We have everything set up. Let's just write it out. Delta G equals, the negative is in the formula, times by the 8.314, times by that temp, 333.15, and then I'm going to times by the natural log, the ln of 0.196. Great thing about using the TI-84 is that you can plug this all in one shot and the calculator will do the correct functions at the right time. So delta G equals negative 8.314 times the number, I'm just going to grab it, reduces error, right? Times the ln, and then I'm going to put in 0.196, close the parentheses, press enter, and beautiful. 4,513, right? And maybe we'll say 0.8 if we're rounding up. Units here would be joule per mole, because those were the two units that were not canceled out. However, delta G's in joules are going to be really, really, really large. So it's good practice to just always convert your joules into kilojoules, because chances are, if it's like on a multiple choice question, they're going to give you the kilojoule answer. So joules to kilojoules, divide by 1,000, just a conversion. So I'll take that answer, divide by 1,000, move the decimal over 3 spots, and now we'll add the correct sig figs. So the temperature I used had a lot of sig figs, and this had only 3. So we're going to use 3 sig figs, so 4.51. And our hypothesis was correct. It is a positive value. That means that at this condition, it's non-spontaneous. So it needs a little extra oomph to actually vaporize water at 60 degrees Celsius. And there you go. Thank you so much for tuning in. I really hope this helped. Let me know in the comments. Subscribe to the channel if you haven't already. Thank you so much. And yeah, let's keep studying hard, keep working hard. You guys got this. I'll talk to you soon. Bye-bye.